What specific problem does the proposed method of repeated sampling aim to solve in the context of large language models? And why is this problem significant in the realm of inference?
The proposed method of repeated sampling aims to solve the problem of improving the reasoning performance of large language models, LLMs, during inference, particularly in terms of coverage and precision when generating solutions to various tasks. This problem is significant because, while larger models have shown improved capabilities, the computational resources allocated during inference have not been scaled similarly, leading to limitations in their performance. By allowing models to generate multiple candidate solutions for a problem, repeated sampling enhances the likelihood of identifying correct answers, thereby increasing the fraction of problems solved, coverage. The findings indicate that with repeated sampling, weaker models can outperform stronger models when given sufficient attempts, making this approach both a performance enhancer and a cost-effective alternative in practical applications. Ultimately, addressing this issue is crucial for maximizing the utility of LLMs in real-world scenarios where accurate and reliable outputs are essential.
How does the proposed repeated sampling method work? Illustrate the process step by step, including any key operations or components that are novel to this approach.
The proposed repeated sampling method works by generating multiple candidate solutions for a given problem, allowing for improved coverage and precision in identifying correct answers. The process begins with a model generating a set of independent samples for each problem, where each sample is produced using the same prompt and hyperparameters. As the number of samples increases, the method assesses two key properties: coverage, which measures the fraction of problems that can be solved using any generated sample, and precision, which evaluates the ability to identify correct samples among the generated outputs. Notably, the method leverages automatic verification tools, such as proof checkers or unit tests, to validate candidate solutions, particularly in tasks like coding and formal proofs. This approach allows for a significant amplification of weaker models, enabling them to outperform stronger models when given a sufficient number of attempts, as demonstrated by the results on various datasets like SWE Bench Lite and code contests.
What are the quantitative results that demonstrate improvements in model coverage achieved through repeated sampling? Can you provide specific examples from different tasks discussed in the paper?
The paper presents several quantitative results demonstrating improvements in model coverage through repeated sampling across various tasks. For instance, in the code contest programming problems using the Gemma 2B model, coverage increased from 0.02% with one attempt to 7.1% with 10,000 attempts, representing over a 300x improvement. Similarly, when evaluating the DeepSeek Coder v2 Instruct model on the SWE Bench Lite dataset, increasing the number of attempts from 1 to 250 raised the solved problem fraction from 15.9% to 56%, surpassing the single-attempt state-of-the-art of 43%. In the math problems, coverage improved from 79.8% with 100 samples to 95.3% with 10,000 samples. These examples illustrate the significant enhancements in coverage achieved through repeated sampling across different tasks and models.
In the context of validation, how does the paper assess the effectiveness of the repeated sampling method? What experimental designs or metrics were used to benchmark its performance against existing methods?
The paper assesses the effectiveness of the repeated sampling method by evaluating its impact on coverage and success rates across various tasks, models, and sample budgets. It employs metrics such as coverage, defined as the fraction of problems solved using any generated sample, and success rate, which measures the fraction of problems solved correctly. Experimental designs include generating a large number of independent samples, e.g., 10,000, for each problem across datasets like code contests, GSM-8K, and math, and comparing the performance of weaker models with repeated sampling against stronger models using single attempts. The results indicate significant improvements in coverage, such as a 300x increase for Gemma 2B on code contests, and a success rate exceeding the single-attempt state-of-the-art by sampling 250 times from DeepSeek V2 Coder Instruct on SWE Bench Lite. Additionally, the paper highlights the limitations of common verification methods, such as majority voting, which plateau in effectiveness despite increasing coverage, emphasizing the need for improved sample identification techniques.
Can you elaborate on the limitations of the repeated sampling methodology as discussed in the paper? Are there particular scenarios or tasks where this method may not be applicable or effective?
The paper identifies several limitations of the repeated sampling methodology, particularly in scenarios where automatic verification tools are unavailable. For tasks like math word problems from GSM-8K and Math, the lack of robust verification methods leads to a significant gap between coverage and performance, as common approaches like majority voting plateau after around 100 samples, despite coverage continuing to increase. Additionally, in software development tasks, the paper highlights issues with flaky tests in SWE Bench Lite, where inconsistent test results can misclassify correct solutions as incorrect. Furthermore, in the code contests dataset, the presence of false negatives due to test cases that do not account for multiple valid outputs can hinder the effectiveness of repeated sampling, as it may require generating a solution that not only is correct but also matches specific output formats. These factors suggest that while repeated sampling can enhance performance in many contexts, its effectiveness is limited in tasks lacking reliable verification mechanisms or where the evaluation criteria are overly restrictive.
What future research directions do the authors propose to enhance the effectiveness of repeated sampling, and how might these improvements address the current limitations?
The authors propose several future research directions to enhance the effectiveness of repeated sampling. First, they suggest improving solution diversity by combining token-level sampling with higher-level approaches, such as conditioning samples with different metadata tags, which could lead to more varied outputs. Second, they recommend exploring multi-turn interactions, allowing models to generate solutions iteratively with feedback from verification tools, potentially increasing solution quality. Third, they highlight the importance of learning from previous attempts, where access to existing samples could inform future generations, especially if verification tools provide feedback. Lastly, they emphasize the need to improve sample verification methods, particularly for unstructured tasks, which would enable repeated sampling to be applied more broadly and effectively across various domains. These improvements aim to address current limitations in sample identification and verification, ultimately enhancing the overall performance of models during inference.